This is tutorial 4B Laplace Transform question 2. In this question, we are asked to find the Laplace transform of sine bt, cosine bt, and e minus a multiplied by cosine bt using direct evaluation as well as frequency shift property. We are however allowed to use this expression over here. The Laplace transform of e minus at equals to 1 over s plus a. Let's begin with the Laplace transform of cosine bt. First, we express cosine bt as sum of complex exponential. This is from ejbt is equals to cosine bt plus j sine bt, as well as e minus jbt equals to cosine bt minus j sine bt. When we add these two complex exponential up, the imaginary part is 0, and we have 2 cosine bt is equals to sum of e plus jbt plus e minus jbt. So this is how we got the expression on the left here. The other thing, once we have this, we can then use the Laplace transform of this individual expression. Since the Laplace transform is a linear operator, it basically means that we can act on the Laplace transform of this individual expression over here. Let's bring the half outside, and individually we get this Laplace transform. The rest then is mechanical. We want to have the common denominator, so we basically multiply the top numerator 1 times s plus jb. This numerator is 1 times s minus jb. We get the numerator on top, and then we see that this cancels, and we have actually 2s, but because we have divided by 2, our numerator becomes s. In the denominator, we have s squared plus b squared if you open up this expression. So finally, this is the Laplace transform of cosine bt. We now do the similar approach to sine bt. Again, we express the sine bt as sum of complex exponential. Here is divided by 2j. Let's see why again. We would use this expression again, however, we're going to change plus to minus. So now we have e plus jbt minus e minus jbt, the cosine disappears. J sine bt minus j sine bt is 2j sine bt. We move the 2j to the other side, and therefore we now have this expression over here. E plus jbt minus e minus jbt divided by 2j. Again, we make use of the property that the Laplace transform is a linear operator. We can act on this individually, and we bring the 2j out. So this 2j is sitting out there. This is the Laplace transform of e plus jbt. This is the Laplace transform of e minus jbt. Again, we want to have common denominator. Therefore, this goes to the top, and we open up the brackets, and we have this. Now, in this case, s minus s cancels. We have 2jb divided by 2j, and therefore we have b on the numerator, and denominator we have this. So this is the Laplace transform of the sine of bt. Now the differentiation of sine bt is equals to cosine bt times b. If we now want to use the property of the differentiation to get the Laplace transform of the cosine bt, what we need to do is apply this expression over here. Let us assume that we have 0 initial condition, so simply we are multiplying S by Fs. But because we are now, when we do differentiation of sine, we have an extra b here, which is not in the original cosine bt. We need to divide it by 1 over b. This gives us s over s squared plus b squared, as what we have over here. So in this example, we could have started the Laplace transform of sine bt using direct evaluation, using the property of differentiation to get the cosine bt. This shows us the power of the properties in Laplace transform. In the next video, we'll answer question 2b of Laplace transform of e minus at cosine bt using the frequency shift property.